Welcome to the next Demystifying Blockchain session, where we'll talk about Ethereum, Corda, and Hyperledger and Enterprise. Sam will go into more details of a comparison of the three, some parallels, as well as benefits and limitations for each of them. All right, over to you, Sam.
Thank you, Julia. So in previous sessions, we've discussed smart contracts and at a high level, the benefits of smart contracts when applied to enterprise environments, how it can enable multiple semi-trusted or untrusted organizations to engage in a business process, financial or otherwise, in such a way that they have guarantees into the execution of that process. And we've also, at a high level, overviewed the different types of blockchain technology, from Bitcoin to Ethereum and Hyperledger Fabric and Corda. And at a high level, Bitcoin and Corda, as we mentioned in the past, have a transaction model that's built around the concept of transaction inputs and outputs, where inputs refer to previous transactions, and outputs specify the constraints for subsequent transactions to spend that transaction. And at a high level, that type of transaction model is ideally suited for financial applications. So there's a concept of a transaction having a state which is spent and putting constraints around how it can be spent. So in Bitcoin, you have each transaction, the inputs refer to other previous Bitcoin transactions, and once a transaction is validated in the blockchain, if one of the validation checks that occurs is it makes sure that no transaction is spent twice. So there's no transaction that shows up in two inputs in the entire blockchain. And by having the constraints embedded within the transaction, so think in terms of constraints, it's along the lines of this, only the individual that has this private key can spend this transaction. By having that constraint embedded in a small Bitcoin scripting language, Bitcoin script, it's ideally suited for the types of financial transactions that you see in Bitcoin. And I bring that up because Corda adopts that same, it's called the unspent transaction output model, UTXO. Corda adopts that same approach from the Bitcoin network, but applies it within a permissioned setting where the identities of the participants are known, and in order to participate in the network, the participants must go through an authentication process. And so what that means is, both in the Bitcoin and the Corda network, you have organizations creating transactions, and as part of the creation of that transaction, they're specifying what inputs there are to that transaction and the constraints on how that new transaction could subsequently be spent at a later point in time. And this is in contrast to the Ethereum model, which Hyperledger Fabric has also adopted, which known as most commonly the account wallet or account balance model. So in the Ethereum model, you create an initial transaction to deploy or install, if you will, a smart contract onto the blockchain network. And so what that means is a developer will write code that describes all of the business logic and rules in that smart contract. So and then they will install this on the network. They'll create a new transaction called a deploy transaction that will deploy it onto the network. And then when they deploy it, that new smart contract, now that it's deployed and running on the blockchain network, the network generates a unique identifier for that. And when a participant wants to interact with that smart contract, they would create a transaction that sends a message to that smart contract using that identifier. And these subsequent transactions that participants generate, they specify the ID of the smart contract that the message should be delivered to. The smart contract receives that transaction, looks at the message, and then determines whether or not the message is valid using the business rules and the validation logic that the developer encoded in the smart contract. And then the smart contract will update its state. So the smart contract has a number of variables, and it has history, and it will update those variables and update the history if the transaction is determined to be valid, where all the rules are encoded in that smart contract. So each subsequent transaction that a participant creates in the transaction message, it doesn't contain, it's very different than the UTXO model, because the transaction doesn't contain the validation rules. The validation rules are contained in this separate program that's been installed on the network, and the transactions only include message payloads that are sent, and the installed smart contract receives those message payloads and executes the business logic. So you can think of it as in the Bitcoin and the Corda case, for every transaction, you're specifying the inputs and you're specifying the constraints on the subsequent transactions, and the constraints are the validation rules. So the constraints are saying this transaction can only be used with another transaction in this way, and you're doing that for every transaction. Whereas in the account balance model that Ethereum and Hyperledger Fabric have adopted, is you write all the business rules and validation rules in a typically much larger smart contract program. You install it on the network as a deploy transaction, and then all the other participants subsequently create new transactions that are sent to that deployed smart contract, and the smart contract then executes the validation rules to determine if those new transactions are valid or not. And so you have one large transaction, the deploy transaction, that has all the validation and business rules, and then you have many typically much smaller transactions that include message payloads that are received by the smart contract, the deployed smart contract, and validated by the deployed smart contract. Now, so in practice, these two different transaction models, really have a lot of implications as to the type of decentralized applications you can build on top of these platforms. And what we find is that the account, has performance and scaling implications, but then also has implications as to the applications that are built on top of this. So in Bitcoin and Corda, that type of transaction model the kind of constraints that are used, because each transaction has the list of constraints in it. So the types of constraints are typically quite small. I mean, you can't. There's so both Bitcoin, Corda, Ethereum, and Hyperledger Fabric, they all have a smart contract language. In Bitcoin, it's Bitcoin script. In Corda, it's based on Java, a domain-specific language that runs on Java or Kotlin, which is you can think of as an alternative to Java that's compatible with Java. And both Bitcoin script and Corda, the constraints are of the form of predicates, meaning when ultimately the way they work is the validation will check to see if a number of constraints are true, and if those constraints are true, then the transaction is valid. So in the case of Bitcoin, it's almost always checked to see that this message contains the signatures that prove that the person has the private key, and then the Bitcoin script program, when it executes, it determines whether or not the signature matches the expected signature in the transaction output. In Corda, similarly, you have a number of, when you write your smart contract in this domain-specific language, you specify a number of constraints that determine whether either it could also be a signature where you're checking to see if. And so in Corda, you can model financial transactions, and you can check to see, okay, does this person have the right signature to receive these funds, or to spend these funds, and if they do, then you allow them to send the funds to someone else. You can have basic, it's a pretty basic language that involves yes or no predicates that are encoded in the transaction. Now, basic meaning like a domain-specific language where you only have a few operations, like checking to see if someone has signed a message, checking to see if they're not trying to spend more funds than are contained in the inputs of the transaction. Those types of kind of true-false comparison, greater than, equal than, subtraction, addition. Those types of specific logic. Now in Ethereum, Ethereum, the key idea behind that as an alternative to Bitcoin was they wanted what they call a Turing-complete smart contract language. So they wanted to go beyond Bitcoin script, where Bitcoin had this very specific financial transaction types of rules. They wanted to go beyond that and be able to do arbitrary computer programs on the Ethereum network, meaning it's not just the case that you're checking to see if you have the right signatures, or you're not spending more than you should be. Go beyond that to be able to write any type of computer program that has a deterministic set of rules and enable more general smart contracts. So this is why you also sometimes hear Ethereum as sometimes being called the world computer, and there's an Ethereum this Ethereum virtual machine where you now write your transaction validation rules in a high-level programming language, not Bitcoin script, which is a domain-specific language, but a high-level programming language called Solidity, or there's a few others that target the Ethereum virtual machine. But you write your programs like you would write, a JavaScript program or a Java program, and those programs have all the rules that determine both whether or not the transaction is valid, but also how to update the smart contract state. And so this is how people build more complex decentralized applications on top of the Ethereum network. So in Ethereum, you have payments where you can, like in Bitcoin, where you can send Ether between individuals, and you can do things like require that to spend a transaction that requires multiple signatures, like you can do it the Bitcoin network. But now you also have people developing everything from gambling applications to games like CryptoKitties, and in some cases, people are putting insurance policies with the Axel Busy project. These types of more general applications, and which could not be built on the Bitcoin network. And so Hyperledger Fabric adopted that same model, but it enabled it in the permissioned and the private setting. Now, I should mention that there are folks that are taking the Ethereum software and deploying it with adding access control on top of that, and deploying it in a private setting. So this is the Ethereum enterprise discussion. There's not an official version of Ethereum that supports all the types of enterprise features that you may need to run it in a private setting. But there are folks that are taking the code that's used for public Ethereum and then running it in private controlled networks, and permission networks, so that they can run Ethereum smart contracts in a private-based setting. And so Hyperledger Fabric was inspired by Ethereum, but what they've done is focused a lot on the consensus algorithms that make more sense in a private setting. So no longer, there's not a cryptocurrency piece to Hyperledger Fabric, and you don't have the proof of work where you require to spend lots of energy to secure the network to come to consensus. But the inspiration of a general platform for smart contracts where you can write regular computer programs that validate transactions, Hyperledger Fabric has adopted that same idea from Ethereum, but applied it in this permissioned setting. So at a high level, one way you can think of this as, in the same way that we now have specialized hardware for doing graphics processing, like GPUs, you can think of Ethereum being a general CPU where it can do arbitrary types of programs that you run on it, and Bitcoin being a specialized type of blockchain for financial transactions, like a GPU is specialized for doing graphics and mathematical operations. Similarly, you can think of Hyperledger Fabric being a general platform for running smart contracts in a permission setting, and like a CPU can run any types of computer programs, and Corda being a specialized version of that for financial transactions in the permissioned setting, like a GPU is specialized for doing mathematics and graphical types of processing. Now, that's as a metaphor. So one thing I should mention is that in all the smart contracts languages, they have to be the programs that are running have to be deterministic. So, this depends on the exact details of that depend on the blockchain architecture. There are some ways recently that people have developed ways of running non-deterministic smart contracts, but for the sake of the discussion and up until recently, all the smart contract programming languages and programs in these blockchain type architectures are deterministic. So they're being executed across multiple. What that means, what the term deterministic means is that there's no randomness, so there's no the calculation of validating the transaction doesn't change given the same inputs. So that's determinism is requiring that a program is deterministic is a pretty strict requirement that most software developers don't have to deal with when they're doing regular computer programming. So to give you an idea, if you have a computer program that tries to get the current time of day, that is a non-deterministic operation. It depends on kind of when you run the program. It requires clocks being synchronized, and as a consequence, in a blockchain type network, that transaction would not deterministically validate it because some nodes may determine that the transaction is correct and others may determine that it's not. And so everything from getting the time of day to generating an ID, a unique ID, which may require randomness, even just communicating with external APIs. So many in kind of modern applications may call a dozen or so APIs in order to compute something where they're accessing some external service. Could be like a Google API or some kind of social network API, what have you. If it's a financial application, you might be looking up a consumer price index or some kind of index, that type of thing, which requires outside communication. And whenever you're communicating externally, that can be non-deterministic. There can be network issues. The website. So both, you may not be able to use the network to communicate with the website. The website might be down. The information on the website may change. So in your smart contract programming language, you can't have non-determinism. So there's a bunch of constraints on what you can write how you write and what you can write in your program. But the biggest one is that it can't directly call out to some other service to get information. But we are creating applications that are processing data from other outside services, and the way we do that is through this concept of oracles, which are regular applications that are sitting off the blockchain network or alongside the blockchain network, and they're creating transactions that contain information to be received by a smart contract, and the smart contract will then validate that the message is generated by the right entity, and then take that data and process it. And so, as I mentioned, in the Ethereum and Hyperledger Fabric world, these oracles can send just arbitrary data to these smart contracts. So maybe it's if it's a consumer price index, every single day, maybe you have an off-chain oracle that looks up the CPI from some government website, encodes it in a predetermined format, and then sends it just that message with a signature to the smart contract. The smart contract receives that CPI, inspects the new indices, and then updates payment amounts, let's say, based on these new indices, and validates that the person who provided the information is someone that the counterparties that are trusting this smart contract trust and agree on ahead of time. So you could have 3 or 4 different insurance companies all agree on a single provider, a third party to provide that input to the smart contract, these CPIs, and then you encode that validation logic in your smart contract so that only that authorized third party can provide the data feed to the smart contract. Now that's very different than, so what I just described is where you have these oracles, and these oracles are calling out and retrieving information and then taking that information and providing it to the smart contract. The smart contract's then processing it. That's very different than how Bitcoin and the Corda type of blockchain or distributed ledger technologies work. So in those types of networks, when you create a transaction, an organization, when it creates a transaction, would include all the constraints, and as part of those constraints, could require a third party to provide a signature that the transaction is valid. So in this type of case, if you were trying to include, let's say, a consumer price index in a Bitcoin type of transaction, then the way it would work is the organization creating the transaction would include that consumer price index in the transaction and then send it to the third party, and the third party would then sign it if the third party agreed that was the right CPI. So instead of the third party directly providing the data to a smart contract, now the third party is receiving a request, and if the third party believes the request is valid, it has the correct CPI, and is maybe doing the payout correctly according to that CPI, then the third party will sign that transaction, and then the transaction would then be broadcast across the network, and the other participants would see, okay, yeah, the third party who's responsible for validating the CPI agrees that this is the right CPI. So it's different because now the third party, these oracles, they're really providing sort of yes or no types of answers to transactions. They're saying, yep, this transaction is valid because, and I'm responsible for checking this part of the transaction. So they're not directly including data in the transaction, but instead receiving transactions and signing them only if their part of the transaction is considered valid. So it's a very different model, and in practice, what it means is if your application is requiring lots of data to be processed, or has complicated validation rules, or requires more than just yes or no types of decisions based on counterparties, then most likely, Bitcoin or the Bitcoin model as adapted by Corda is going to be difficult for you to include all of those validation and business logic rules or data processing logic rules. But what it also means, though, is that in some cases, the Corda and the Bitcoin model can be easier to scale. So at a high level, really, what we're coming up against is sort of two different philosophical viewpoints on scaling, where in one camp, the Ethereum, the Hyperledger Fabric type of camp, the philosophy is really to put more complexity and put more on the blockchain network, so that you have this visibility, you have like auditability, you have non-repudiation and verification of all of the validation and the execution of the smart contracts, and everyone can see into that. Whereas the Bitcoin and the Corda type of model, that philosophy is more, no, you take as much as you can off the blockchain, and the blockchain becomes more of either a settlement or a verification layer of processes that have been executed off the blockchain. So there's sort of, it's easier if the blockchain network, if all the nodes in the network are doing less, then you can process more and it's easier to scale. But the trade-off is that you don't have as much visibility into these processes that were executed off-chain. So there's sort of philosophical scalability argument on the side of keep the blockchain in Bitcoin and Corda, keep all the execution of these business processes and smart contracts off the blockchain. Let the blockchain that the smart contracts were executed correctly. Whereas in Ethereum and Hyperledger Fabric, no, you have the network do the validation, execute all the smart contracts. You have many nodes in the network executing these, validating every step, but you're going to have a harder time executing many smart contracts and many transactions. So there's a scalability argument. There's also this also has implications for confidentiality. So if in the Ethereum and the Hyperledger Fabric case, in the most kind of basic setup, we can do other sessions where we dive deep into like Hyperledger Fabric and the different and confidentiality in particular in these different types of networks. But in the most basic kind of configuration, Ethereum and Hyperledger Fabric, you have all of the nodes validating and executing all the smart contracts and transactions. And that's a benefit because of the visibility and transparency, verification of the execution, all of that is a benefit. But what it also means is that everyone can see all the data that's being processed in the most basic kind of configuration. So there's sort of a trade-off between confidentiality. So you can verify things, but then also you can inspect and see the data that's being verified, sort of necessarily so. Which means that in these applications, all the participants should be allowed to see the data that's being verified and processed. Now, in the Bitcoin and the Corda type of case, because a majority of the execution and the data processing in your application is being conducted off-chain, and on-chain you're just simply doing verification that, let's say, these counterparties are in agreement at this point in time over something, then the details of the execution and processing off-chain are not necessarily exposed to the entire network. So data becomes less visible, for better or worse, to the other participants in the network. So you might have, so in Bitcoin, some of the original, to give you an idea of this, like some of the original Bitcoin gambling applications, the way they worked was there would be a trusted third party that would be responsible for signing transactions based on who won, let's say, a horse race. And then up front, you would have the counterparties create the transactions to send their funds to the other counterparties, and they would create all these transactions up front, but the transactions would have what's called a multi-sig requirement, meaning they're only valid if this trusted third party signs it and the counterparty signs it. And so they would then send these unsigned transactions to the trusted third party, and then depending on the result of the horse race, the trusted third party would then sign the correct transactions and broadcast that to the network. And so you can think of that as sort of a decentralized gambling application on top of the Bitcoin network, even though the Bitcoin network only supports very simple, this multi-signature type of Bitcoin script smart contracts. So the execution, the determination of who gets paid happens off-chain, but the verification and the payment happens on-chain. And and in some cases, these other transactions that were created of sending money to that were created by all the counterparties, only one of those transactions gets broadcast to the network. So all these other transactions that were not signed and do not get broadcast to the network remain sort of invisible to the network. No one else in the network sees these other transactions except the direct counterparties and this trusted third party. And Corda takes that similar type of approach, inspired by that Bitcoin model, transaction model of these unspent transaction outputs, where you can have these counterparties work with the trusted third party, and then the trusted third party would only broadcast one of possibly many transactions that were generated when necessary. Another way you can think of this is you could have off-chain, you could have multiple parties creating transactions with each other and agreeing on each step of a process that's being executed. And then only when something goes wrong does one of the counterparties broadcast a transaction on, let's say, the Bitcoin network. So this is how the Lightning Network, if you're familiar with in the Bitcoin world, how that works, where you have microtransactions being conducted off the blockchain, and then periodically, or if something goes wrong, someone will broadcast an off-chain transaction that gets turned into an actual Bitcoin transaction, typically penalizing the person who broke the rules of the protocol. So, in terms of scaling, in the Bitcoin and sort of Corda case, you're having many more processes being executed off the blockchain, and then using the blockchain to verify those execution when things go wrong, and the other participants not having any real visibility into what's going on off the blockchain, but also not seeing the details. Whereas in the Ethereum and Hyperledger Fabric case, you have everyone on the network seeing each execution step and seeing everyone agree on the execution of that smart contract in all the details at each step of the way. So it's different benefits and trade-offs, and the technology choice is really going to depend on the type of application you're building. But I would say a general heuristic would be for a public payment financial type of transaction, Bitcoin is probably what you'd be looking at. For a private kind of financial type of transaction that's similarly payment related, where you maybe check a signature or two, making sure that you have the right number of signatures, making sure that someone's not spending more than they have. In a private setting, Corda would be a good fit for that. Whereas if you're developing a public decentralized application that's processing data or making or having validation rules that go beyond checking multiple signatures, checking that an account that you're not spending more than you have, so maybe you're processing the data somehow or triggering multiple triggering external events that are not payments related, that type of thing, then Ethereum would be a good fit. Or if it's more of a permission in a private setting, then Hyperledger Fabric would be a better fit. So think like if you have some business process that's receiving data from multiple touch points, manipulating that data, triggering payments based on the details of this data, where the logic is including multiple factors, then you're looking at a blockchain like Hyperledger Fabric being a better fit for that type of application. So at a high level, there's sort of general and specialized blockchain architectures. more general, where you have Hyperledger Fabric and Ethereum in the general camp and specialized in Bitcoin and Corda. You can think of it as how in hardware you have CPUs and GPUs, where CPUs are a more general piece of hardware that can execute arbitrary computer programs, and GPUs are very specialized to doing mathematical operations. There's this concept of oracles and how oracles can provide information to a business process. We like so many of the applications that Luther System is building, we like to think of our smart contracts as railroads and connecting different stations. And these different stations would each run oracles that are providing data to the smart contract, where the smart contract then receives that data and processes it and triggers the communication with other stations based on these railroads, where the railroads are the agreed upon rules set ahead of time. So there's the station type of oracles that I just described, but then you also have, in the Bitcoin and the Corda case, these very specialized types of oracles where they're making yes or no decisions. So they receive some kind of request, a transaction, and they're saying, yep, this transaction is valid, or no, the transaction is not valid, and they're doing that just by inspecting what's already contained within the transaction. We talked about Ethereum, how it's applied in the public case, but then also how some people are using it in a permissioned and a private setting to run the same type of smart contracts that would be run in the public network. We talked about Hyperledger Fabric and Corda, and we briefly went over some of the benefits and drawbacks of the different technologies based on this architectural choice of the transaction model, where with Corda and Bitcoin, you have the unspent transaction approach, and with Ethereum and Hyperledger Fabric, you're looking at more of an account balance based approach. Thank you.
Thanks a lot, Sam. That was very insightful. I have just two more questions because you answered everything else actually during the talk. So quite in the beginning, you mentioned the different languages that have to be used. And I was wondering, on a very practical side, is it the case that one developer then can only develop, for example, for Corda or only for Hyperledger? Or is this are there different languages, but in the end they're very similar, so that usually when you know one, you can also do the others? So I'm asking that because it's more on the practical side, and I think that might come up more often also with clients, as in general there's not that much expertise yet in developers in that space.
Yeah, it's a good question. So there's sort of a theoretical answer to this question, where theoretically they're equivalent, but from a practical standpoint and a performance standpoint, what can actually be built, mm-hmm. If your business logic and your validation rules is being executed by all the participants, and it's sophisticated, and it goes beyond checking a signature, checking that you have, let's say, M of N or 2 of 3 signatures, or checking that some number is less than some other number, performing if it goes beyond those type of simple checks, then you're going to need a smart contract language like Solidity in Ethereum, or in Hyperledger Fabric. You can write your smart contracts in Go or mm-hmm. in JavaScript. These are high-level computer programming languages that developers are familiar with and write. Outside of blockchain technology, they write applications in these languages all the time. Whereas in Corda, it's a very specific language like Bitcoin script is, where you're limited to these very basic checks. So from a practical standpoint, it makes a huge difference. But theoretically, you can prove Turing completeness of some of these really limited domain-specific languages. So theoretically, you can make an argument that they're equivalent, but from a practical standpoint, Bitcoin script or the Corda domain-specific language would be too limited for something that goes beyond just basic signatures and addition and mathematical operations.
Okay, I understand. Thanks. And at the end, you actually went into a bit more detail in which type is best for what kind of application. So I was just trying in my mind to abstract out some main criteria on how to decide for the ideal one. And the ones I've just had in my mind based on what you've mentioned would be whether it's a public or private network, whether it needs to scale, the number of transactions that go through